Good day, everyone. First of all, thank you so much for spending time to attend my presentation today. Now, permit me to start my presentation. My presentation is about ultrasensitive strain sensor enhanced by bonded light emitting diode. My name is Thanh, and we are from the Griffith University and University of Southern Queensland, Australia. So my presentation today includes five main parts. The first is research background, the second is sensor operation principle, and the third is fabrication and experimental setup, and the fourth is result and discussion, and finally is the conclusion. Now permit me to start with the first constant. So the strain sensor is one of the most popular sensor, one of the most mechanical sensor. It were used in different applications from robotic, smart city, structural health monitoring, mechanical adjustment, automobile industry, environmental monitoring, energy harvesting, and other applications. For the strain sensor, piezo resistive effect is one of the most popular sensing concepts using in strain sensor because of simple readout circuit, sensor with small size and good linearity, and easy to integrate. So the piezo resistive effect is defined as the chain of electrical resistance under applied strain state, and the piezo resistive effect equality by the K factor is calculated as the equation on the slide. So there are different ways to improve the performance of the strain sensor. For example, we can optimization the orientation of the piezo resistor, or optimization the doping concentration, or using the material with the better piezo resistive effect. And also we can scale down the size of the piezo resistor to nanoscale. For the flexible or soft electronic, we can enhance the microstructure chain of the strain sensor. And recently, some researcher using multi-physics effect to coupling to enhance the performance of the strain sensor. And you can see in the table in the slide either when we using the different method, so the K factor of the strain sensor is significantly improved. So recently, our group had using the optoelectronic coupling in a heterojunction to enhance the performance of the piezo resistive effect, which have been published in the Nature Communication. So for this one, usually for the conventional, we use to enhance the performance of the piezo resistive effect, we use combine between the night illumination. The night will be non-uniformly to the sensing element, and we also coupling with using the tuning current to enhancement the performance of the piezo resistive effect. And by using the optoelectronic coupling, the performance of the piezo resistive effect has been significantly improvement. For example, as you can see on slide, under the dark condition, the K factor of the silicon carbide on silicon heterojunction is about 20, and under the night condition with the optimal tuning current, the K factor of the heterojunction structure have been improved until to 58,000. This is approximately 3,000 times improvement. So however, for our previous publication, we using the external night source to illuminate the sensing element. So this is a disadvantage. So there is one question: are there any integrated light source which is suitable to use for the optoelectronic coupling? So we conduct this research using the LED as an integrated light source to enhance the performance of the sensor. So as you can see on the slide is the sensor operation principle. So for this one, we use the LED as a light source to illuminate to non-uniform illuminate the sensing element, and we supply the tuning current to comply with the light illumination to enhance the performance of the piezo resistive effect on the silicon carbide on silicon heterojunction. So to investigate the performance of the sensor, the first step we fabricate the sensor. So in this slide shows the fabrication process of the strain sensor. So the first process is grow silicon carbide on silicon wafer, and the second is the deposit and pattern the silicon dioxide on the silicon carbide layer, and after that is a deposit and pattern the metal electrode on the top of the silicon carbide and the silicon dioxide layer, and after the pattern and deposit and pattern the metal, the sensor, the wafer will be dyed to form the cantilever, and from the cantilever the LED will be bonded on the top of the cantilever using a adhesive bonding method. So here is a experimental setup. So for investigate the performance of the strain sensor with the geometry as cantilever. So the cantilever will be clamped at the one end, firmly clamped at the one end, and the node will be applied on the free end, and the net will be powered by a DC power supply, and the signal the signal will be measured using the semiconductor analyzer, and simultaneously the semiconductor analyzer will be used to tune the current. So for the investigation, we will investigate both the natural photovoltaic effect to make sure that the night illumination from the LED is suitable for using in the optoelectronic coupling. As you see on the slide, is we investigate the IV curve and the generated of the lateral photovoltaic and the photocurrent, and you see that is the photocurrent and natural photovoltaic is big, is not enough for using in optoelectronic coupling. So for the formation of the lateral photovoltaic effect is a generation. It combines of the electron hole pair generated in the under the night illumination, and the injected of the hole into the silicon carbide, and the diffuse of the hole on the silicon carbide layer, and it creates the gradient of the carrier concentration on the top the silicon carbide layer. And after that, we investigate the performance of the of the sensor, and you can see here the performance is a comparison between the performance of sensor under the night and the dark condition. And you can see here is the performance of the sensor will significantly improve from between when using without the LED and with the LED. For example, without the LED, the gate factor of the change sensor is at 20. However, with the LED and the tuning current, the gate factor is around 18,000. And the significant enhancement of the piezo resistive effect due to the bonded LED is contributed by 3 key factors. The first is the illumination from the bonded LED, which then create a gradient of Hole concentration. And the second, the electrical field which created by the tuning current redistribute the major carriers on the silicon carbide layer. And the third is the mechanical strain deviate the sub-valence bands under the for example, under the tensile strain, the energy subspan of the heavy hole shift up, and then to lower hole energy level, and the energy subband of the night hole move down to higher energy level. We already successfully fabricated a strain sensor with bonded piezo LED, and we also successfully investigate the performance of strain sensor under different conditions. So with the strain sensor, we can using the bonded LED coupling with the tuning current, the sensor, the gate factor of the strain sensor have been significantly increased from 20 to 18,000. So finally, thank you very much for your attention. So if you have any question, please contact me via the email on the screen.